So we have two different molecules here. This is hydrogen peroxide. We call it peroxide because it has this oxygen-oxygen bond. And here we have oxygen difluoride, where oxygen is bonded to two different fluorines. And what I want you to do is pause this video, use this periodic table of elements I have here. And this is more than just a typical information in a periodic table of elements. It also gives you the electronegativities of these different elements. And these electronegativities are based on the Pauling scale, named after famous biologist and chemist Linus Pauling. And so using the information here and what you know already about oxidation states, think about the oxidation states or the oxidation numbers for each of the constituent elements in these molecules. So pause the video now. So I'm assuming you have given a shot at it, and you might have immediately realized that something very interesting is going on. We've said in the past that oxygen typically, because it's two valence electrons away from a full valence shell, because it is so electronegative, oxygen typically takes electrons from other things, typically 2 electrons, which typically gives it an oxidation state of negative, an oxidation number or oxidation state of -2. This is so electronegative and it so typically oxidizes other things that we've called the whole phenomenon oxidation. But what's interesting here is that oxygen isn't purely bonded to things less electronegative than itself. In the hydrogen peroxide, yes, it is bonded to the hydrogen, but it's also bonded to another oxygen. Obviously, these two are going to be equally electronegative. So what would be the oxidation states or the oxidation numbers here? Well, hydrogen, once again, we pretend hydrogen, because it's less electronegative, it would have a partially positive charge because the electrons would spend more time around this oxygen. But when we're talking about oxidation states, we don't like this partial charge business. We want to pretend like these covalent bonds are ionic bonds, hypothetical ionic bonds. And if they were hypothetically ionic bonds, what would happen? Well, if you had to give these electrons to somebody, you would give them to the oxygen, the electrons in this pair, you'd give them to the oxygen, giving it an oxidation state of -1. With the hydrogen having these electrons taken away, it's going to have an oxidation state of +1. And the same thing is going to be true for that oxygen and that hydrogen right over there. So this is fascinating because this is an example where oxygen has an oxidation state not of -2, but of an oxidation state of -1. So this is already kind of interesting. Now it gets even more interesting when we go to oxygen difluoride. Why is this more interesting? Because fluorine is the one thing on this entire table that is more electronegative than oxygen. So in our hypothetical, this is a covalent bond, but in our hypothetical ionic bond, if we had to give these electrons to one of these atoms, you would give it to the fluorine. So the fluorine, each of them would have an oxidation state of -1. And the oxygen here, now you can imagine this is nuts for oxygen. The oxidation state for oxygen, it's giving up these electrons. It would be a +2. When we talk about oxidation states, when we write this little superscript here, we write the sign after the number, and that's just the convention. But it has an oxidation state of +2. Oxygen, the thing that likes to oxidize other things, it itself has been oxidized by fluorine. So this is a pretty dramatic example of how something might stray from what's typical oxidation state or its typical oxidation number. And in general, oxygen will have an oxidation state or oxidation number in most molecules of -2, but unless it's bonded with another oxygen or it's bonded to fluorine, which is a much more electronegative, or actually not much more, but it's the only atom that is more electronegative than, or the only element that is more electronegative than oxygen.